Hello, everyone. We are pleased to be here with you today to talk about AI-driven network design at Renault Group. So our masterclass will divide in three parts. First, I will present you the business case. Then Siham will go into the details on our in-house optimization tool, and I will finish with some key takeaways and perspectives. So let's start with the business case overview. Renault Group has been shaping mobility since 1899 and now is becoming into a next-generation automotive company. With our four brands, Renault, Dacia, Alpine, and Mobilize, we are driving innovation into a smarter, more sustainable future. After Renault 5 and Renault 4, now it's the turn for Twingo to make its comeback. If you haven't seen it, go and check it out. Innovation doesn't stop there. Supply chain plays a key role on this transformation, ensuring agility, sustainability, and performance. We operate in a rapidly changing environment, and we manage a very complex supply chain, as you can see with the numbers in the screen. Four main activities are related to our supply chain. The first one is capacity risk management to ensure a resilience on our supply network. The second one is parts logistics to bring all parts from suppliers to our production sites. The third one is sales and operation planning processes. And the last one is vehicle logistics to bring cars to our customers everywhere in the world. Today, we are going to focus on a key activity on part logistics and vehicle logistics, the network design. It is the core activity of our engineering teams. It is a strategic process to design and optimize the whole company network. We take several decisions, such as the location, the role of the sites, and the product flows between those sites, both parts and vehicle logistics. And we have two main objectives: to meet customer demand and to minimize costs, transportation cost, storage cost, carbon emission cost, you name it. And network design is far more complicated on the automotive than most industries. And let's see some points on why. First, for part logistics, cars are extremely complex products. Thousands of parts need to be delivered from suppliers to plants in a just-in-time environment in a global supply chain. Our sites have a capital-intensive footprint, so changing them of location, it's very expensive, and we have a big demand volatility. For vehicle logistics, we have a bulky, high-value products. The transportation sector for vehicle logistics is a very constrained one. There is not enough capacity for all the demand. We have a global distribution footprint. We deliver cars almost everywhere in the world. And we have also demand volatility. And all of this with a huge economical stakes, over €1 billion transportation budget per year. That's why we developed a digital solution based on data and AI to help engineering teams on their decision-making process on network design. Three main enablers: Dataiku, Google Cloud Platform, and Spotfire. We started developing a web application in Dataiku so that business users can set up their simulation. We launched a pre-processing in Dataiku that gets the information from the users, but also all our data that is stored in the data lake. We prepare the simulation, and then we send it to our operational research algorithm, which Siham will detail for you in a few minutes. The results come back to Dataiku, and we do a post-processing, which we send back to our data lake so that we keep the historical trace. And the final user will go to a Spotfire report to consult the results, to do some analysis, and finalize his decision-making process. We have worked on this solution for the past 2 years, and in November of 2024, we delivered the solution for the network design parts logistics, around 1 year of development. And Last September, we delivered the second solution for vehicle logistics, which was developed much faster because we capitalized on everything that had been done on the first solution. Let's take a look on the specificities on input data and pre-processing. It is a big challenge, and you would tell me data is always a big challenge on AI products, but there are some specificities here linked to network design. First of all, one of the main inputs is the demand, the future demand, and we are not talking about the next week future demand, we are talking about long-term demand, which needs a big data quality so that the algorithm works correctly. The second one is the master data. All master data related to network design is not necessarily available in our systems. Imagine some transportation legs we don't use today. We don't have necessarily how much would it cost. So we use machine learning algorithms to complete missing data. The third point that is very important is that we need to create the potential network. We know how parts and vehicles go through our network today, but we want to explore new possibilities, and we need to have a big transformation data preparation to create this potential network. But if we give a lot of possibilities to our algorithm, then the optimization will take a lot of time. And if we don't explore enough on the potential network, then we might miss some potential optimization. So it is a key part of the data processing. And the last one, and it is also very important for adoption for business users, is that we need to show them the as-is network with its costs, and we need to show them the optimized network, evaluating it with exactly the same business cost model. So those are the four main challenges related to input and pre-processing. On the left side of the slide, you can see how it looks on Dataiku. It is a small part of all the flow in the platform, but we use the low-code possibilities both for machine learning and data treatment. So now let's imagine you are engineering working on Renault on vehicle logistics, and you arrive in the morning and you want to use the application. I hope it works. So yeah, you connect to Dataiku, and the first thing you want to do is to set up the parameters you want on the simulation. Here you have some structural things you can change. For example, avoid the flows to go through a specific point because it's the analysis you want to do. You have also, so it's what the person is doing right there. I don't want vehicles to go through this specific node. You have some other things. You can restrict the number of intermediate sites in the simulation, and then you can name the parameters regarding your choice. You can have as much parameters as you want. Then you go to the simulation screen, and then you choose the geographical scope you want to optimize. You choose the plant, one or several plants, the country, one or several countries, and you choose the parameters you just set up so that the simulation takes into account. You can choose some other things, like the time limit on the algorithm, if you want to restrict that part. And then you click on the button. OR algorithms will start, and you can go and do other things. And once the simulation is done, you see it in the screen, but you'd also get an email so that you can come back and see the results. As I said, the results, you can consult them on Spotfire report, which show you, as I said, as-is network and optimized network. And then you have some economic KPIs that allow you to see how well went the optimization. In this case, we can do 2% of profit if you put in place the proposed network. But then you will have to analyze more in detail with some specific routes and some filtering you can do directly in the Spotfire report. And also you can have some even more detailed information if you want to proceed to put in place with the transport companies the optimized network you just simulate, or you can come back, change some parameters, and relaunch the simulation. So this is the first part we wanted to present you, the whole view of the business case. Now let's open the hood for optimization tool with Siham.
So, yes. Thank you, Christian. So let's continue the story of this tool from a technical point of view. The network design outbound use case is a challenge. Sorry, I see that. Okay, yes. It's a business challenge, and it's also a technical challenge. And we stand it up this way, and this is how we usually work together with Christian. First, we start with the development of a prototype to check the technical feasibility, to provide a demonstrator to the key users, to get quick feedback, and to make quick wins. When we achieve the prototype purpose, and if we decide to go on, then we develop what we call the minimum viable product. This one will be deployed in production environments. The MVP can bring more functionalities and sometimes less functionalities than the prototype. And once the MVP is validated, then we switch off the prototype, we let the MVP between the hands of the key users, and we adjust the functionalities of the tool, and then we can scale it up. This is our third and last milestone. Today, I precise that because I know that POCs sometimes are criticized, but in our case, in our units, 90% of our prototypes go on and finish as a production application. Let's keep in mind, I don't know if it works well, but let's keep in mind that during the whole process, our two teams stay continuously in touch. And when we start working on the minimum viable products, specialists from DevOps teams, from architecture teams, from cybersecurity join the projects and bring their contribution to build a robust tool. We will focus now on the engine part. So what we want to do is to minimize the transport cost of all our vehicles from all the plants to all the car dealers. And we know that the shipping costs are different if we use trucks or boats or trains. And we also know that the shipping costs increase with the traveled distance. So that means that a tool can play on these two aspects to target our optimization objectives. And the tool, of course, must provide feasible and realistic solutions that will respect all the real-world constraints. In few words, we want to minimize costs subject to constraints. And in the wide AI landscape, the operational research deals with this kind of problem. The operational research techniques, melting mathematics and computer science, are specifically designed and developed to search for feasible solutions and for optimal solutions to problems like that to help us in decision making. Sorry. Here I share with you my vision of the optimization of operational research strengths, weaknesses, opportunities, and threats. And there's no error. I mentioned frugality in the both sides. Technically, frugality is a real on business side also. It's a strength, but sometimes it can be also a weakness. In 2 words, what I would say about OR is just that it provides a powerful toolbox that has proven its effectiveness And as we are in France, I should mention that we have a very active community in the field, and it's a dynamic field, with the support of the scientific French association ROADEF. Je ne sais pas pourquoi il passe. Sorry. So, when we use OR techniques, we first start with the translation of the business use case into a mathematical model. Here we define the decision variables. We identify the optimization problem category. We start to choose the OR techniques which are appropriate for our problem. We evaluate also the complexity level, and etc. And then we implement the mathematical model algorithm, and we run the optimization solver. And at the final step, we write the output results in a practical form for the users. In our case, our algorithm takes as input data the list of plants, the car dealers, the list of possible routes, the cost of the routes, the volume we want to deliver during this period. And it produces, as a result, the optimized network, which will be defined by the optimized route for each volume of vehicles and the optimal transport mode for each route. And of course, it provides also an important KPI, which is the global transport costs. Let's have a look on the algorithm. So this slide is a high-level view of the algorithm implemented by the team, as shared by the team for this event. So thanks to them for that. What I can say is just here we have used two OR techniques. The first one is a local search approach to solve what we call a relaxed problem. And we use for that a French solver, which is the Exali solver. And then, based on this first result, we implement a heuristic which will ensure that the solutions are feasible in respect of all the constraints. We develop our application in Java. We package it in a Docker image ready to be deployed. So today, our optimization engine is deployed on Google Cloud Platform to benefit from the scalability of this kind of infrastructure. And I think it's already adopted today by the key users, thanks to the quality of the optimized solution, and thanks, as mentioned, to the ease of use of DataIQ and Spotfire to see the results and take the business decision. So now I'm going to give back the floor to Christian for a few words about the conclusion.
Thank you very much, Siham. So, okay, we have enough time. Might finish a little bit earlier. So let's go for the key takeaways and some perspectives on our work. So we have seen during our presentation that network design in the automotive industry is much more complex than in most industry because of the characteristics I mentioned at the beginning. It is at the heart of our engineering team's activities, and we chose to develop an in-house AI-driven decision tool with some web application and all the details we got on operational research algorithms, which enables smarter, faster, and more resilient supply chain. They are used since November of last year and September of this year for both parts and vehicle logistics. We mentioned a big challenge on data quality as for all AI modules, but with the specificities on network design side and automotive industry. those are critical for AI adoption. We can tell you, start small, do pilot projects, do some proof of concepts, because those will allow you to validate with key users, business key users, which need to be there since the beginning. And we have had a lot of interactive loops with them before getting to the solution that we present to you today. But POCs are not enough, especially because we developed the algorithm and we work with some key users that are really motivated, so they accept that there is no big ergonomy or that things work in a specific context, but we need to scale. And to scale, we need to industrialize. And to industrialize, we need to bring much more teams than our teams, DevOps, architecture, technical architecture, and so on. And you need also to package the algorithm with robust and best-in-class solutions such as Dataiku for the interaction with final users and all the data treatment. So that's what we did, and that's one of the key successes on our project. In conclusion, our strategy is to profit of our AI expertise internally to build an in-house solution using or leveraged by best-in-class enablers. So we have similar projects that were developed with a similar approach. We have an algorithm that helps to optimize the truck loading, and it is connected to our plant's MRP, and it runs every night. We have vehicle routing algorithms, decision-making tool, more on a weekly basis decisions that is used in several countries in Europe by around 20 people since several years. And we are working on a dock scheduling algorithm to optimize the arrival of trucks at our plants. All those were developed with the same approach, and we can say that today we have, for the transport planning, we have our homemade TMS at Renault Group. We talked a lot about operational research, and it's definitely what has given us a lot of profit around these topics. But we have some perspective on using machine learning. I mentioned a little bit on missing data, but we have some other perspectives. For example, to improve the transportation need forecast, I mentioned that we have a 2, 3, 5-year forecast. So the more this forecast is accurate, the better results on the optimization we will get. And we work with Cermix Laboratory on the Col des Ponts, Paris Tech, on hybrid approaches on machine learning and operational research, in which in the algorithm we use both techniques and we get better results. And better results mean better optimization, which means more business value, which is what we are seeking here with this kind of initiatives. And we need to talk about it because I think everyone talks about it. So agentic AI could help business to create scenarios with natural language, or where some context that is given not by choosing the parameters, but with some other ways on natural language specifically. And again, the Cermix Laboratory is starting to explore some agentic approaches to make collaborate different OR, operational research algorithms. As I said, we have a lot of them that are used at different moments in our planning process. We could use agentic AI to make them talk and get better results. Obviously, we want to use agentic if it shows business value, which is still need to be confirmed. Thank you very much for your attention.